The Netflix series The Three-Body Problem is filled with intriguing ideas that would capture the curiosity of anyone interested in science. Among them, the most captivating is the story of a civilization inside a virtual world. The main character, a brilliant physicist, Jin Chung, is invited to play a VR game designed by San Ti Ren, where she encounters multiple civilizations in succession. Her mission is to save these civilizations from destruction by predicting chaotic era of extreme solar activity and stable era where life can thrive. To achieve this, she must calculate the movement of sun. The civilization inside the virtual world mobilized over 30 million people to create a massive human computer. Yet even then, they still fail to make accurate predictions. Jin Chung eventually realizes that the problem is fundamentally unsolvable. This planet has not one, but 3 suns, making it nearly impossible to predict the movement of these interacting bodies. This is the very problem that gives the series its name, the three-body problem. What makes this problem so fascinating is that despite being based on Newton's well-known laws of motion and universal gravitation, it remains unsolved. The two-body problem, where only 2 objects interact, is simple. In such cases, when 2 celestial bodies, like the Earth and the Sun, are bound by gravity, their orbits can be precisely calculated as ellipses, circles, or hyperbolas. But once a third body is introduced, everything changes. The 3 bodies pull on each other with gravity, constantly shifting their positions in unpredictable ways. As a result, their orbits become increasingly tangled and chaotic, making long-term predictions nearly impossible. Why does this happen? The reason lies in the equations governing three-body motion. They are nonlinear differential equations. A nonlinear equation is one in which relationships between variables go beyond simple addition or multiplication, often involving more complex operations like squares or exponential functions. One of the most important characteristics of nonlinear equations is that they may not have a single definitive solution. Even tiny differences in the initial conditions, down to just a few decimal places, can cause vastly different outcomes over time. This sensitivity to initial conditions is the essence of the three-body problem. Even the slightest variation grows exponentially, leading to complete unpredictability over time. Anyone with an interest in science might be thinking, this sounds familiar, doesn't it? And that's right. The concept of chaos, which originates from the three-body problem, later evolved into chaos theory, famously represented by meteorologist Edward Lorenz's discovery of the butterfly effect. It is a deterministic system, yet so complex and sensitive that long-term predictions become nearly impossible, and that is the world we live in. If the three-body problem alone is this chaotic, then how difficult must an n-body problem be? We don't have to look far. Our own solar system is an n-body problem. Fortunately, our solar system is relatively stable. Unlike the San Ti planet in the series, which undergoes cycles of destruction, our solar system's stability has allowed life to emerge and civilizations to flourish. But according to chaos theory, even this stability cannot be guaranteed forever. In 2009, scientists used supercomputers to simulate the future of our solar system. By slightly tweaking the initial conditions, they calculated the solar system's motion over periods ranging from 500 million to 5 billion years into the future. Most scenarios remained stable, but in about 1% of cases, Mercury's orbit was thrown into chaos, leading to a collision with Venus or even falling into the Sun. What's astonishing is that the researchers adjusted only one initial condition: Mercury's distance from the Sun. That distance? Less than 1 millimeter. Can you believe that a difference of less than 1 millimeter could determine whether a planet crashes into another or spirals into the Sun? This proves that even our solar system is a massive n-body system, where chaos is always lurking beneath the surface. Does this mean that in the face of the chaos, there is nothing we can do? Not at all. In the 19th century, the French mathematician Henri Poincaré studied the three-body problem and mathematically proved that a general solution applicable to all cases does not exist. But that doesn't mean we can't find solutions at all. Scientists have discovered specific solutions that apply to specific cases. One of the most famous examples is the Lagrange points. A Lagrange point is a position in space where the gravitational pull of 2 large celestial bodies and centrifugal force balance each other. If a small object is placed at one of these points, it can remain stable, as if it were fixed in place. Of course, such specific solutions are rare. However, advancements in computing have made it possible to approximate solutions even for complex equations beyond these special cases. This method is called numerical analysis. By leveraging immense computing power, we can break down a continuous orbit into extremely short time intervals, calculate motion for each segment, and then piece them together to estimate the full trajectory. This method is widely used not only in astronomy, but also in weather forecasting, financial market analysis, and many other fields where n-body problems frequently arise. The inherent chaotic nature of the world has always stood in the way of perfect prediction. Yet, in our own way, we have sought answers, strived to understand the world, and struggled to survive within it. We are painfully aware of how small our existence is in this vast universe, and that is precisely why we believe there is still something yet unseen, something we must continue to learn and explore. That is the greatest power of science, the reason we look forward to its future.